let us continue. So, what I was talking about just before the break was the concept of gauge transformations. You see, we replaced we introduced the 4 vector A mu as a succinct representation of Maxwell's equations. And then we introduced the concept of electromagnetic field tensor. Now, the point is that the A vector or the A mu vector that we have introduced is not uniquely defined. In other words, if I transform A mu by the expression that is given in the green box here, my electromagnetic field tensor remains unchanged, and therefore, my Maxwell equations still continue to be satisfied. So, that gives us a certain amount of leeway or a freedom or ambiguity in terms of the representation of the 4 vector A or the that we can use for the purpose of representing the electric and magnetic fields, right. So, now we try, however, we to arrive at a unique representation, we therefore need to impose certain restrictions, to impose certain gauge requirements. One of the gauge requirements that we impose is called the Lorentz gauge. In the Lorentz gauge, what we require is that the expression within brackets here, within the curly brackets here, in the green box at the bottom of the slide, this should vanish. That is the requirement of the Lorentz gauge. Let us see what it implies. If we have this requirement, which is here in the red box here, what we end up with is the expression that is in the green box at the bottom of the slide after simple algebraic manipulations. And for the vacuum, we have an expression of the form box of A nu is equal to 0. Now, we talk about the fundamental fields in nature are the spinor fields that are leptons and quarks, and gauge fields that we are talking about just now, and also gluon fields. But in the case of electromagnetic field, we have only 2 independent components in contrast to 4 independent components which are required for a covariant representation in 4 dimensional space time for a single particle. So, that being the case, we are faced in a quandary which in some sense also makes its presence felt, which also manifests itself in the gauge freedom that we have just talked about. So, we really have 2 choices. We have the choice of choosing 2 of these components as the physical components and then quantize those 2 components, but in this case we lose Lorentz covariance. And on the other hand, the other choice that we have is that we treat the 2 components as redundant and we retain Lorentz covariance. Let us do the first approach. So, to recall then, the electromagnetic field tensor we had defined in terms of the expression that is given in the red box here, and the 4 dimensional curl, and as I mentioned, the d mu of the or the derivative of the first 4 dimensional electromagnetic field tensor is equal to the J nu, the components of the current, and this encompasses the inhomogeneous equations, and the homogeneous equations are automatically satisfied from the property of the electromagnetic field tensor being a 4 dimensional curl. In vacuum, what happens, the right hand side disappears and we have the expression which is given in the green box at the bottom of your slide, which we have already discussed. For the Lorentz gauge, we write the Lorentz gauge in the form given in the red box here. We have seen that this expression leaves the electromagnetic field tensor unchanged. We impose the condition given in the red box here, and what we end up with is for the Lorentz gauge, if we impose this restriction that is given in the red box here, then on simplification what we find is that the derivative of A dash mu, that is the transformed A mu, takes the form which is given here in the blue box. And if you simplify this using the expression in the red box here, what we find is that we have d mu A dash mu is equal to 0. Now, if we drop the primes, we get the expression for the Lorentz curve that we want to impose, that is d mu of A mu is equal to 0. So, this is the Lorentz gauge or the Lorentz condition that we want to impose in our analysis. So, a vector potential satisfying this condition, that is d mu of A mu is equal to 0, is said to belong to the Lorentz gauge. This one condition, this one restriction reduces the number of independent components from 4 to 3, but we are still not unique. Why we are still not unique is because if any scalar function satisfies the requirement given in the red box here, the box of eta x is equal to 0, then what we find is that the condition or the Lorentz condition is automatically satisfied. Therefore, this gives us another, there is still some non-uniqueness remaining even after the imposition of the Lorentz gauge. For this purpose, we impose the Coulomb gauge to make the definition unique. How we do it? We impose the following requirement, which is given in the red box here. The time derivative of the scalar function is equal to minus phi, and when we do that, what we get is that phi goes to phi dash, and what we get for a dash 0 is equal to 0, and for A, for the spatial part of A, we get minus delta del A, that is the divergence of A, 3 divergence of A is equal to 0. In other words, the Coulomb gauge is specified by the expression in the green box, that is phi is equal to 0, and the divergence of A, the spatial A, is equal to 0. These two together make the Coulomb gauge, but please note they are not relativistically covariant. So, we are now left with only 2 independent components of A mu, and this is the case of the real world where we work. So, working in the Coulomb gauge, or this is also called the radiation gauge, we retain the physical nature of the electromagnetic field. Now, the Lagrangian of the Maxwell equation, we shall be dealing with it when we talk about the path integral, is given by the expression in the red box here, but we will be coming back to it. The canonical quantization in the Coulomb gauge, we start with the Lagrangian which is given in the red box here, from which by a variational principle we can derive the Lagrange equations, and we define the conjugate momenta in terms of the expressions that is given in the yellow box and the expression in the green box. The time component of the conjugate momenta vanishes, and the spatial component of the conjugate momenta represent the electric fields. And therefore, the quantization commutator that we desire, or we attempt, or we postulate, is given by the expression here in this slide, which is self-explanatory. So, let us carry on. And although there is a small problem here in the sense that here the indices, if you look at the second commutator, the indices are upstairs, whereas I and j indices are upstairs, whereas on the right hand side of the equation the I and j indices are downstairs. And secondly, the appearance of delta I j instead of the flat metric eta I j or g I j is also makes it relativistically incorrect, but numerically of course it turns out to be correct. However, when we look at these commutators in the context of the Coulomb gauge, we find that they are inconsistent with the Coulomb gauge, because if we take divergence of both sides, divergence of delta A is equal to 0, divergence of the spatial A is equal to 0, as you will recall in the case of the Coulomb gauge. So, if I take divergence of both sides, what I get is that the commutator is unequal to 0, which is not compatible with the Coulomb gauge. and therefore this commutator is required to be modified. To modify the commutator, we write delta ij by capital delta ij, which we now postulate as a second rank tensor symmetric in I and j, and we also write the delta function in 3 dimensions in terms of the Fourier representation as shown in the green box here. When we take divergences now, we find that the divergences would vanish when the condition imposed in the yellow box is satisfied, and the condition imposed in the yellow box would be satisfied when the condition imposed in the green box is satisfied, that is when capital delta ij is equal to minus small delta ij plus ki kj upon k squared, k special squared. So, the revised commutators now take the form which is given in the slide. The upper red box covers the commutators between ai and ej, that is the ej represents the conjugate momenta and ai represents the field variables, and the others are of course the commutators between similar quantities. Now, we come to the electromagnetic wave equation. Maxwell equations, as you recall, is given by the expression given in the first expression in terms of the electromagnetic field tensor. In vacuum, of course, there are no sources, so the right hand side vanishes, no currents are there, so the right hand side vanishes, and in the Lorentz gauge, the term in the round brackets in the green box also vanishes. So, what we are left with is box of A nu is equal to 0. Furthermore, in the Coulomb gauge, the time component of A also vanishes, phi is equal to 0, and therefore, we have the box of the spatial A is equal to 0. This is nothing but absolutely similar to the Kleene-Gordon equation for the massless field. The solution of this expression is given in terms of the fundamental solutions, exponential wave vector solutions, exponential ikx and exponential minus ikx, and these are called the coefficients of course must be vectors called polarization vectors, and we denote them by epsilon superscript lambda k, where lambda is a label. Now, therefore, we write, as in the case of scalar fields, we write A x as the expansion in terms of the creation and annihilation operators as in the case of the Kleene-Gordon equation for the scalar field as shown in the red box here. In this case, because m mass is 0, so k square will be equal to 0, k 0 will be equal to mod of k, and k will be equal to plus minus of k 0, that is the spatial k will be equal to plus minus k 0, and lambda can take only two values 1 and 2, since in the Coulomb gauge the divergence of A spatial A gives 0, and that gives the condition that required in the green box with k because k can take only two values, therefore, lambda can also take only two values here. And that is compatible with the fact that the photons or the massless spin 1 particles travel with the speed of light and have only two independent components. Now, if we define to get the expressions for the creation and annihilation operators, we can define functions in terms of the expressions given in the red box here, in which Ax can be represented in the expansion given in the green box at the bottom of the slide, and because these functions f kx, these are there in the red box here, are orthonormal, so we can recover straight away the expressions for the creation and annihilation operators as the expression given in the blue box and the green box at the bottom of the slide. And the commutators between the creation and annihilation operators are can be easily worked out as straightforward and are given in this slide. To reiterate, the Coulomb gauge which is shown in the red box here is not Lorentz covariant, and hence in a sense we lose Lorentz covariance while working in the Coulomb gauge. Now we come to the most important topic here, the path integral quantization. The generating functional in the case of quantum electrodynamics, that is the electrodynamics of the electromagnetic field, will take the form that is given here, where L is the Lagrangian, the script L is the Lagrangian, which is given by the expression in the right side of the red box, and J mu are the respective sources, A mu are the field variables, and this Lagrangian or this generating function has been written in consonance or in line with the expressions, with similar expressions written for the scalar fields and the particle and the free particle in the quantum mechanical case. Now, the variation of the Lagrangian in the electromagnetic field tensor is the Lagrangian is this, and if you do the variation of this Lagrangian, we can recover the Maxwell field equations which are given here, and these Maxwell field equations can also be represented, as we have discussed again and again, in terms of the electromagnetic field tensor in this form, in the form given in the green box here at the bottom of the slide. Now, starting from this expression that we brought forward from the previous slide, if we multiply by G mu nu the metric, the flat metric in this case, we get please note throughout we are representing the flat metric by G mu nu, although in many references they use eta mu nu. So, but here we are using G mu nu as the flat metric, and we are using the convention of plus minus minus and minus. Now, multiplying by G mu nu, we get the Maxwell equations as the expression that is given in the blue box, and which can be written in the form which is given in the green box here. Simply some algebraic simplifications, multiplying by G mu nu throughout and doing some algebraic simplifications gives us the expression that is given in the green box here at the bottom of the slide. Some manipulations of indices, nothing more here. Now, from this set of Maxwell equations which I got from the previous slide, we can recover the Lagrangian in the form which is given in the green box at the bottom of the slide. Now, let us look at the photon propagator. What is the behavior of the photon propagator? What happens to the photon propagator corresponding to the Maxwell equation that is given by the expression here in this green box here. Now, corresponding to the Maxwell equation that we had in the previous slide, that is this one in the green box here, the photon propagator should be the green function of the Maxwell equation, and therefore we must have the expression here in the green box must be satisfied, because this is the Maxwell equation in the red box, and my photon propagator d mu nu must be the green function of this particular equation, and that leads us to the expression that is given in the green box at the bottom of the slide. Now, let us explore what happens here. If we multiply both sides by d of mu, or we differentiate both sides take the 4 derivative of both sides, what we get is with some manipulations of indices, some careful manipulation of indices, we find that our propagator turns out to be singular, because the left hand side's coefficient vanishes, the coefficient of the propagator vanishes, and although the right hand side does not vanish, and that means that the propagator is singular. And this is why does this happen? Because this operator that is given in the red box here has no inverse, and because this operator has no inverse, we have to adopt a certain detour to arrive at the expression for the propagator, we multiply by del mu eta. On multiplying by del mu eta we get 0, which in fact shows further that the operator has 0 eigenvalue and therefore has no inverse. So, it is explicitly shown by the expression in the green box that this operator here in the red box has 0 eigenvalue and hence does not have any inverse. So, what do we do? Now, why is this happening first and then what do we do? We have the expression for Z0, that is the normalizer, as the expression given in the red box. Now, the important thing is that, as we mentioned earlier, the entire theory is invariant under gauge transformations of the form that is given in the green box. Now, but when we are working out this integration is taken over all of A mu, including those which are related to each other by this gauge transformation given in the green box. In other words, there is some sense of overcounting going on, and as a result of which the contribution to Z is infinite, because a particular potential would be counted again and again because of the gauge freedom that is allowed between or in defining a potential A, and therefore this particular problem will give an infinite contribution to Z, and as a result the green functions that would be obtained from this particular path integral or the generating functional will also be infinite. So, we need to do gauge fixing here, as we did in the earlier case. We need to do a gauge fixing before we do the path integral quantization. As we discussed, the gauge fixing that is normally done is the Lorentz gauge and followed by the Coulomb gauge. So, what we do is we impose the Lorentz condition given in the red box here, and now when we impose this Lorentz gauge, condition given in the red box here, the Lagrangian becomes the second term in the Lagrangian. If you look at it, the second term in the Lagrangian vanishes, and we can write the Lagrangian in the form which is given in the expression in the green box here. Now the operator, in contrast to the earlier situation, if you look at this operator G mu nu d mu or G mu box has an inverse, and the inverse is given by the Feynman operator. You can see that in the red box here at the in the slide. So, by imposing the Lorentz gauge, we can write the Lagrangian as this form, and we now have a non-singular propagator, and furthermore because this expression in the round brackets is equal to 0 in the Lorentz gauge, the Lagrangian can be modified and it can be written in the form that is given in the red box here, where the first term is L0, L script 0, which is the Lagrangian of the free field, and the second L script GF, the subscript GF represents gauge fixing. In other words, L script GF represents the gauge fixing term in the Lagrangian. In momentum space also we have a similar catastrophe, similar problem. In the momentum space, this becomes the expression that is in the red box here, and again this expression has no inverse in the momentum space, and that is established in the slide by, because if there were to exist an inverse, it would be of the form A capital A into A V mu nu plus B k nu k lambda, and on taking the products of this inverse and the original operator, we should have delta on the right hand side, but this equation has no solution. So, the net outcome of this is that the expression expression that is here in the red box does not have a inverse. In the Lorentz case, however, the operator minus g mu nu k square, that is the first term. If you can eliminate the second term by by introducing the Lorentz gauge, the first term has the inverse given in the blue box, and the Feynman propagator being the green function is given represented by the expression that is given in the green box here. Of course, we can generalize what we have done earlier. We may add to the Lagrangian an arbitrary amount of the gauge fixing Lagrangian. Instead of having L gauge fixing, we can have a coefficient, a scalar coefficient attached to it, and we can write the Lagrangian in the form in a generalized form, which is given in the red box here, and which gives us the expression given in the, which is equivalent to the expression given in the green box here, where alpha is a finite expression. The corresponding expression in the operator in momentum space is the expression that is given in the red and green box here, red and blue box here, and the inverse is given by the expression given in the green box here. Now we come to the transverse photons. Now this propagate, we have not introduced the Coulomb gauge yet. Now let us talk about the Coulomb gauge. The propagator given by this expression, which is obtained after putting in the, or after introducing the Lorentz gauge. This is now the Lorentz gauge is a covariant gauge where the polarization vector epsilon mu has the scalar product between the wave vector and the polarization vector equals 0, and therefore only 3 states out of the 4 are independent. But as we know that there are only 2 independent states of the photons, and therefore we are still a little bit away from getting a physically viable expression for the propagator representative of physical photons. For this we introduce the Coulomb gauge. As we discussed earlier, the Coulomb gauge represents is represented by the time component of the 4 vector potential being 0, and the divergence of the spatial component of the 4 vector being 0, and the relation between the propagator and the relation between the propagator and the 2-point function is given by this expression. This is the 2-point time ordered product of the field variables. Remember, in the electromagnetic field, the A's are taken as the field variables. So the expression in the blue box is the time ordered product of the field variables, and on the right hand side we have the expression for the propagator. Now you would recall that we had obtained the expression for a mu of x earlier in this lecture in the form that is given in the red box here, and it is in terms of the free waves or e to the power ikx and e to the power minus ikx with the polarization vectors. So what do we have? We have on the one hand, when we introduce these expressions in the expression for the time ordered product, when we introduce the expressions for a mu x and a nu y, when we introduce these expressions in the form which is given in this slide, in the red box here in the slide, and we take note of the time ordering represented by the theta functions, the Heaviside functions, what we get is the expression in the green box here. So this is simplified, and what we get is the expression in the in this whole slide. This entire slide is the simplification of what we had in the previous slide in the green box here at the slide. Now the terms in A dagger, A dagger can be replaced by their commutators, and then delta functions can be introduced, and delta functions after introduction they can be integrated over, and once they are integrated over and then they are summed over lambda. So, there are a number of steps involved here. The terms involving A dagger, you replace them by the commutators, and replacing them by the commutators will involve introduction of delta functions, integrate over these delta functions, and then sum over lambda, and the expression that we get is the expression that is here in the slide. The Feynman propagator for the massless particles has the expression which is given here for y equal to 0 for and a given x. It is given by the expression in the green box right at the bottom of the slide. So, we now have two expressions connecting the time ordered product and the Feynman propagator. Both of them are here on the slide. On the one hand, the time ordered product has been represented in the form given in the first equation, and in the second hand, the right hand side of the time ordered product is related to the expression given in the yellow box here through the Feynman propagator's expression. So, combining the two and simplifying and using the explicit expression for the Feynman propagator, we get the expression that is given in the green box at the bottom of the slide for the propagator for transverse photons. So, with that we conclude this segment relating to the path integral formalism of quantum mechanics and quantum field theory. From here on we will be taking up the final segment of this course that will relate to the financial applications of the path integral formalism. Thank you.